Greetings everyone, I am Karan Ahuja, a fourth-year PhD student at the Human-Computer Interaction Institute of Carnegie Mellon University. Today, I'm going to talk to you about my project Vid2Doppler, which utilizes mmWave Doppler radar for privacy-preserving human activity recognition. This work was done with my collaborators Jiang, Mayank Goel, and Chris Harrison. mmWave Doppler radar is a new and promising sensing approach for human activity recognition, offering signal richness approaching that of microphones and cameras, but without many of the privacy-invading downsides. This is because unlike images and audio, which can tell you what the person looks like or the contents of their speech, the mmWave radar sensor returns a radial velocity across distance map. This has made it very popular for ranging and pedestrian detection-based tasks for autonomous driving. For example, the signal on the right here shows that something 4 meters away from the camera is moving at 0.7 meters per second in the direction of the sensor. For the purpose of activity recognition, we want to characterize and identify these motion profiles, and one of the best ways to do so is to train a supervised deep learning model. This is an example of different activities and the number of samples of each class across them. As you can see here, unlike audio and computer vision approaches that can draw from huge libraries of video to train deep learning models, Doppler radar has no existing large dataset, holding back this otherwise promising sensing modality. We considered possible sources of training data, including depth camera and motion capture datasets, but these were much smaller than equivalent video data sources, such as the YouTube 8M, which alone has 250,000 labeled video instances spanning across 1,000 classes. Thus, we set out to create a software pipeline that converts videos of human activities into realistic but synthetic Doppler radar data. Our synthetic dataset consists of 10.4 hours of data curated from different video datasets highlighted in the table. Here is an overview of our software pipeline, which we will cover. The first step of a processing pipeline is to take an input video and fit a 3D mesh to humans in the scene. We can then position a virtual camera to synthesize any view of the user. This simple manipulation, essentially a form of data augmentation, means we get a multiplicative effect on every second of input video. Next, we estimate the magnitude of reflected RF and any induced Doppler shift by computing the radar cross-section and radial velocity of each vortex in the mesh with respect to a virtual Doppler sensor. We then perform backface culling and also account for any occlusion from the user. Now, left only with vertices that are visible to our virtual sensor, we can compute a holistic synthetic Doppler signal by summing all the individual vertex reflections. The envelope of this initial simulated Doppler signal roughly follows that of actual Doppler data. However, the correspondence can be greatly improved with an encoder-decoder model trained with real-world data. This is the final output of our pipeline and what we use to train convolutional neural networks for activity recognition. Once trained, our model can predict activity using live Doppler radar data as seen here. This model, which recognizes 12 exemplary activities, was trained solely with data drawn from public video datasets. Note that the video of the user shown here is for reference only, and our approach is only using the Doppler radar data for recognition, which is much less privacy invasive. Here, you can see a few more plots of the synthetic and the corresponding real-world Doppler signal. To evaluate our system, we collect data from 10 participants over 12 activities. When we train our model on the synthetic Doppler data generated from the videos and tested on real-world Doppler data we collected in our user study, our system has an accuracy of around 81%. When we add real-world Doppler data into the training mix and run a leave one participant out cross-validation, the accuracy increases to 93%. While our approach is more privacy-preserving in comparison to cameras and microphones, the logging of activity data in itself can cause privacy concerns and implications. Such concerns would have to be mitigated by privacy-aware design choices by consumers and manufacturers alike.